Okay, here's the second free response on the circular motion test. And so I'm going to scroll it down so you can just check things out on your own. But if you want some more help with it, I'm going to go over in some detail here. You still may have some questions, so feel free to talk to me live and in person about these. And so here we have a turntable, and it's spinning with some angular velocity omega, and we want to put a coin on it. Coin has a mass big M at a distance r over 2, so it's halfway out right here. And we find that it's just about to slip if we spin this at this particular angular speed. So if I spin it any faster, the coin would slide. And so from that, we want to determine the coefficient of static friction, mu s, between the coin and the disk in terms of these and fundamental constants. Fundamental constants for us pretty much is always going to be little g or big G, and no big G in this one, so little g. And so we draw a free body diagram of the coin, and I draw it when it's here, but I'm drawing it from the perspective of somebody looking sideways. So you can see the normal force up, the weight is down, and static friction toward the center of the motion. I indicate my coordinate system, and so a well done free body diagram worth a point here. Sum of the forces in the y equals 0. Normal force minus the weight equals 0, so the normal force equals the weight. It was okay to just state that. Sum of the forces in the x equals ma, and the only force in the x is static friction. And the mass is big M, and the centripetal acceleration is omega 0 squared times r. And so that's the other version of our centripetal acceleration equation, omega squared r, or I can use v squared over r, but in this case, since we're given omega, we want this one. So I put that in, and the force of friction, since it's just about to slip, is at its maximum. So remember, normally it's less than or equal to, but when it's just about to slip, it's equal to mu times the normal force. Before then, it's only as big as it needs to be, right? And then we know the normal force, so I put that in. So that's friction. So solving for static friction, the maximum static friction was worth a point. Put that into there. And we get the mass canceling out. And solving for mu static, then I get omega 0 squared times big R over 2g. And I wanted everything in terms of omega 0 and big R. Now, you should have had the mass cancel out, but if you had everything else right, I didn't take off if m was still in there. And so you got a point for the correct answer, and then a point for knowing the centripetal acceleration was this. Remember, it's r over 2. You put in what the actual value is, and that's r over 2. So let's move on to the next part. So that was worth 4 points, and we saw a lot of problems like that one, but yeah, it's harder without numbers, maybe. Some people think it's easier, but should have been able to get most of that. Free body diagram was key, as it is here. And so now we're going to move the coin out to here. And so it's going to be harder for it to stay on, because the acceleration is omega squared r. As r increases, for the same omega, I get more acceleration, I need more force. But before, it was just about to slip when it was here, and so now it's going to slip off for sure. And I don't want it to. It's this really nice gold coin, and so I tie a string to it, and the string is attached to the middle. And so the string keeps it on, and I want to know how much tension is in that string. So a free body diagram now looks just like the previous one, but there's a second force, the tension, acting toward the center. And so this part is the same, N equals mg. Force of friction is the same. It's just about to slip. And so I want the minimum tension in the disk. Friction's at its maximum here. Some of the forces in the x, I have this extra term for the tension. And so this now is m omega 0 squared r, because the radius is r. It's not r over 2. And I can substitute in what I know friction for, And again, a lot of this you did in the previous part if you got to this part. And so solving this for tension, I get this, but I'm not allowed to have mu in my answers. So I take in whatever answer I had from part A and substitute in. And so I took the omega 0 squared r over 2g, and so the g cancels out, and I can simplify some, and I get m omega 0 squared r over 2. And so that was worth 3 points here, 1 point for a correct free body diagram, but almost everybody who got this correct was able to do the rest of it. So if you think free body diagrams aren't worth learning how to do, they're crucial to getting problems like this right. Now, if you were able to do it right without the free body diagram, yeah, you get the 3 points. But if you're having trouble, learn how to draw these correctly. And so 1 point for having Newton's second law here with the substituted centripetal acceleration, and 1 point for solving for the tension in some form out where you substituted for a mu. And so if you made some algebra mistakes or didn't simplify it, you still could get the 3 points here. And then finally, we have a projectile problem. And so the string is cut, so the coin slides off. We know it's going to. And we want to figure out how far it will go before it lands, how far in the horizontal direction. And so it is going tangentially, and so we are looking, I guess really it would be here when it comes off. And so it's coming, you know, out of the screen. But we're looking from the side here, and so it's going at whatever speed it was going as it left, and that's omega 0 times r, and I want to know how far in the x direction it goes. And so the y motion, y is 1/2 at squared, v0 is 0 in the y direction, v0y is 0. And so the height is given as h, and so the time to land is square root of 2h over g. And then the x motion, x0 plus v0 xt, and v0x is omega 0 r. And so you got 1 point for figuring out the initial x velocity, 1 point for solving for the time, and this was key to doing that correctly, and then 1 point for putting those two together. But any time you had, if you messed up over here, as long as you took whatever you got here and whatever you got here and multiplied them and didn't do anything else, you got that 3rd point. Okay, we are done.